So hi everyone, welcome to this tutorial on non-convex optimization for high-dimensional signal estimation, spectral and iterative methods. My name is Yuejie. I'm a faculty at Carnegie Mellon University. This proposal is put together by myself and my colleague and collaborator Yuxin Chen at Princeton, and Cong, who's currently a postdoc at UC Berkeley, but will be joining University of Chicago as assistant professor next year. To begin, I'd like to first thank our students and collaborators whose contribution and discussions have contributed to shape our understanding of this topic. And we would like also to thank our sponsors, without whose support this work won't be possible. As an outline, this tutorial will contain 4 parts. So this particular part will be the introduction part, which will discuss the motivation of why we would like to have non-convex paradigms for signal estimation. And we'll go over some basic concepts in optimization and use a warm-up example on PCA. Second part will be given by Professor Yuxin Chen, who's going to talk particularly about gradient descent and its a phenomenon called implicit regularization that often implies very fast convergence of gradient descent for some challenging non-convex problems. The third part will be covering spectral methods, which can either be used as an important initialization strategy for iterative solvers such as gradient descent, or used as a standalone estimator, which is the case, for example, for problems such as community detection. Finally, the last part will talk about important generalization of the non-convex paradigm to make it more robust to corruptions and yield conditioning in the context of low-rank matrix estimation. So without further ado, this part of the tutorial will be focusing on the part 1. So non-convex estimation problems are everywhere in signal estimation and data science. We're dealing with empirical risk minimization problems by formulating it as an optimization problem where we're searching for some parameter x to minimize some loss function constructed using the data. And this can be seen for applications such as low-rank matrix completion, blind deconvolution, dictionary learning, deep learning, and so on. Often, the classical view of the non-convex optimization are often quite pessimistic. Even for very simple objective functions constructed, for example, using a one-layer simple neural network, we know there are data configurations where there may be exponentially many bad local minima in the loss function. So that meaning optimizing such an objective function can potentially be NP hard. Another example for such pessimistic view can be seen from this example called maximum cut for a graph problem, which is about solving a quadratic problem where the goal is to find some indicator vector that contains entries either 1 or -1 to maximize certain quadratic loss function with respect to the graph adjacency matrix W or Laplacian matrix. Now, this problem turns out to be NP hard in general, so that we do not actually have a computational tractable solvers for solving such a non-convex problem. One possible strategy to bypass such pessimistic view is result to convex relaxation, where you can do this by either coming up some convex surrogates for the objective of interest. One example that we will talk about is in the context of the matrix completion application. Another possibility is using the so-called lifting trick, which lifts the object interest into a higher dimension, such as in the application of max cut. Okay, so just to illustrate this convex relaxation approach, consider the application of matrix completion, which is also the canonical model beneath the very famous Netflix challenge. So the problem here is consider we have some data rating matrix for objects of interest, where we think of the rows of this matrix as ratings from different users, and columns this matrix as ratings for different objects. And in typical applications, we only have a small number of ratings corresponding to the observations that the user may read certain movies that they may have watched. And the goal is to predict the unseen entries in this matrix. So hopefully, by predicting these entries, we will be able to provide better recommendations for the user. Okay. Now, this problem, unfortunately, is quite ill-posed in general without posing any structure about this matrix. One possible structure that is often very practical in practice is to model this matrix having certain low rank structure, where the spectrum of this matrix decays very fast. So you may think about this assumption is essentially saying that the predictions in this matrix can essentially be explained by a small number of factors. Okay. Now, this basically, put in other words, means this matrix can be roughly thought as well approximated by some low rank matrix. Okay. So the question is now, how can we exploit this approximate low rank structure in prediction, specifically in estimating the missing entries in this matrix? One popular paradigm that has been set forth now about more than 10 years ago is to use this approach of convex relaxation, where we want to relax this rank constraint into its convex surrogate. So, which effectively turns into a semi-definite program where the goal is to find some matrix M with the smallest nuclear norm subject to some data constraints along the lines of observations. Okay? Indeed, this type of ideas and its robust variations, it has been actually used by Netflix and has been quite successful. However, one drawback of this is that often we need to be solving a quite expensive optimization problem over the full data matrix space, which can be quite expensive, even though we know this matrix has certain low dimensional structures. Another example for this type of convex relaxation idea using the lifting idea is this for this max cut problem. So recall the formulation of the max cut problem given in the slide. We're now going to define some higher dimensional matrix object capital X, which is the outer product between X and X transpose. Therefore, the dimension of this capital matrix X is much larger than the original vector X we are interested in. With this in place, we can now effectively rewrite the original optimization problem with respect to the small x into this equivalent optimization problem with respect to the capital matrix X. By also writing down some of the constraints about them into the diagonal entries about this matrix, as well as its positive semi-definite constraint, and also another non-convex constraint that constrains the rank of this matrix X to be 1. Okay, so if we omit or cancel out this rank 1 constraint, the rest of the problem is essentially a convex one. So that by relaxing the problem, we can basically now end up solving a convex optimization problem instead. Now, again, the issue with this approach is we have an explosion in dimension where we significantly increase the dimension of the unknowns by doing this lifting. Okay. So with the possible drawbacks of non-convex relaxation, a natural question is, how about we directly solve the non-convex optimization without doing any of this lifting and convex relaxation? Now, indeed, in practice, people have been solving these non-convex problems on a daily basis, very, very simple algorithms such as stochastic gradient descent or gradient descent, which seems to be implying that despite the challenges that we face in theory by some of these conventional wisdoms, the simple iterative algorithm seems to be work just well in practice. And we want to understand why, right? Why is this the case? It seems non-convexity is maybe it's not too difficult or it's not too daunting. Now has been a quite recent line work that tried to reconcile the gap between theory and practice, particularly by bringing into the picture the role of statistical models. So what we are going to argue here is the data we are facing in practice are typically not adversarial, but maybe are generated by certain statistical models, at least some postulated ones, so that we can actually argue about the average case performance of these problems, which can sometimes turn out to be having much more benign landscapes in terms of optimization. And so that even with very simple algorithms, we can actually solve this problem very efficiently. And indeed, often under certain statistical models, we are able to see some benign global geometry of the loss function, in the sense there are no bad spurious local minima, so that all the local minimas are actually corresponding to the global minimum of the objective function. On the other end, we don't have challenging saddle points in the loss function, in the sense we only have what we call strict saddle points, so that if you are on these saddle points, you can always find some direction where you can probably decrease the loss function quite effectively. So therefore, as long as you can converge to a local minima, you are also guaranteed to converge to the global minima of this type of problems. And therefore, with this in mind, even the simplest possible non-convex methods might be remarkably efficient under suitable statistical models. Okay. Indeed, this line of thinking has been quite fruitful in the last couple of years. And in this slide, we only have documented a very small sample of some early works in this literature, where we've seen the development of provably efficient non-convex optimization algorithm for solving problems such as phase retrieval, matrix completion, blind deconvolution, dictionary learning, robust PC, and so on. And the list is still growing. And the goal of this tutorial is essentially try to understand some of the basic literature in this growing field, and so that you may also use them in your own research. To begin, we'll start by talking a little bit about the basic preliminaries in optimization literature. All right. So to begin, the primarily in this tutorial, we'll be considering an unconstrained optimization problem. We're going to search for a parameter x to minimize certain loss function f of x. Typically, if you are using some simple gradient-based algorithms such as gradient descent, you'll be typically converging to some critical points, which we are going to define. Okay, so the first one we are going to look at is what we call the first-order critical points, which corresponding to data parameter x where the gradient is 0. Okay. Moving one step further, we are also going to be interested in the so-called second-order critical points, where a second-order critical point satisfies the fact that the gradient at this point is 0, and also the Hessian at this point is a positive semi-definite matrix. All right. Okay. So there are typically several types of critical points we'll be interested in. Assume you are running, say, some sort of gradient-based algorithm, and you reach to a stationary point that corresponding to a first-order stationary point where the gradient is 0. And then you can examine the situations of Hessian to further divide about which type of first-order critical points you have. So for example, if the Hessian is negative definite, this means you are at a local maximum of your loss function. If your Hessian is positive definite, this means you are at a local minimum of your loss function. If your Hessian has this property that the smallest singular value is the smallest eigenvalue is strictly smaller than 0, then you are at the so-called strict saddle points. So what this means is that if you're at this type of strict saddle points, and if you can identify the eigenvector corresponding to the smallest eigenvalue, So if you move your parameter along this eigenvalue functions, this eigenvector function directions, you can probably guaranteed to decrease the loss value and therefore escape this strict saddle point. Okay. Now let's also look at a little bit about what kind of convergence guarantee we can argue for this simple iterative algorithm called gradient descent. Particularly, we're interested in the scenario where we can achieve fast convergence, meaning the convergence rate is geometric or linear. In order to enable such convergence rate, standard optimization theory, particularly convex in the context of convex optimization, often requires two types of property. The first one is some sort of local restricted strong convexity, or sometimes regularity condition, which we'll soon define. And another condition is sort of the local smoothness. Okay? Putting them together, often we require the Hessian of the loss function in this sort of local neighborhood needs to be positive definite and also being well conditioned. More precisely, we're going to say the loss function is an alpha strongly convex function and beta smooth if the Hessian is lower bounded by some alpha times identity, where alpha is strictly positive, and upper bounded by beta times identity. Okay, now with these two parameters, we can guarantee that gradient descent will essentially guarantee to contract at a linear rate in terms of the L2 error if you set the step size to be inversely proportional to the smooth parameter beta. And the convergence rate is essentially going to be determined by the so-called condition number, which is the ratio between the smoothness parameter beta and the strong convexity parameter alpha. Okay, so in particularly, if you want to be epsilon close to the optimal point, you can do this within a number iterations that is on the order of the condition number times log 1 over epsilon. All right. Now, another very important condition that is also applicable to non-convex problems is the so-called regularity condition. Now, we are going to say of some function g. So this g, essentially, you can think of this as a negative direction via search direction. It satisfies this regularity condition for some parameter if the inner product between this g of x and your descent, the distance to the optimal point, is going to be lower bounded by some fraction of the norm of g plus the distance, the square distance between your x to the optimal point. Okay. Now, with this regularity condition, we can essentially get a very similar contraction rate for the gradient descent update, gradient descent type update, where we are updating on the negative direction of this vector g. Okay, where the convergence rate is determined essentially by the product of the parameter mu and lambda. Now, I want you to think about this search direction g as something more general. If you are doing vanilla gradient descent, then you can think of this g essentially as a gradient. But more generally, this will apply to a problem where the g can be more generous than just the gradient. Such, for example, in a non-smooth problem, this can be potentially the subgradient, and sometimes can be even more general. Okay. And again, the product determines the rate of convergence. In order to achieve epsilon accuracy, now the iteration complexity depends on essentially on 1 over mu times lambda. Okay. Now, to connect the regularity condition to the type of strong convexity and smoothness condition we are familiar with in the context of convex optimization, you can think of regularity condition as a relaxation in the sense we're going to relax the strong convexity to one that we call the one-point strong convexity. We're only requiring this type of strong convexity holds where we are going to fix one point to the optimal, while allowing the other point to be changing, essentially around some parameter space of interest. Okay, and on the other end, we will have the typical beta, the smoothness property as following. Okay, so these are just standard properties, consequence of the smoothness property. And if you combine this together, you end up with this regularity condition, where you can see basically this parameter mu is roughly the same on the order 1 over the smoothness parameter, and lambda is essentially the strong convexity parameter. So again, now we see that the regularity condition is essentially relaxation of the strong convexity, where we only require one point strong convexity pointing towards a global optimal point. Okay, so with this basic optimization preparation in place, we can now think about a toy non-convex problem, which is quite simple, but nonetheless, we will highlight some of the key ideas that will be proven useful for some more complicated problems later. Okay, so in particular, we'll be revisiting this problem called the PCA problem. And for simplicity, we'll be thinking about just a positive semi-definite matrix. For example, you can think of this matrix coming from computing maybe the sample covariance matrix, which is always a positive semi-definite one, but not necessarily low rank. And the PCA problem essentially tries to find its best rank R approximation, which can be written as the following non-convex optimization problem, where we're finding some matrix C that is closest to the matrix M in Frobenius norm, subject to a rank constraint, where we're enforcing this matrix to have a rank strictly smaller than R. Okay, so this problem is non-convex due to this rank constraint, but nonetheless, it is actually a very tractable problem, where we know from the Erkin-Yang theorem, this problem actually admits a closed form solution, particularly if we write down the eigenvalue decomposition of the matrix M, where we order all the eigenvectors and eigenvalues in a decreasing order, then the solution to the previous problem, PCA problem, can be essentially found by just taking the top R component from this eigen decomposition, where we only retain the top, the largest R eigenvalues and the corresponding eigenvector outer products, and removing the rest. Okay, so this toy example is already a testament to the fact that even sometimes we have non-convex problem, but that does not necessarily always mean the problem is NP hard and is not tractable. We may well have non-convex problems that are tractable. Okay. Now, from now on, we're going to imagine throw away our understanding about this closed form solution to our PCA problem, but rather now resolve this problem from an optimization perspective, which will be useful for us. Okay. Now, to think about this from an optimization angle, we're going to invoke this matrix factorization approach, that we are going to rewrite this matrix C by its classical decomposition as XX transpose, where the matrix X is going to be a tall matrix factor that contain only R columns, where I is the rank of this matrix. Okay, so by rewriting the matrix C into this factorization model, the rank constraint is automatically satisfied. Therefore, we can rewrite the PCA problem into an unconstrained optimization problem with respect to the matrix factor X. Okay. Now, despite that we have removed the constraint, now we'll end up with a loss function that is non-convex, which is quite obvious because we can not identify the matrix factor X uniquely, but only up to some orthonormal transform. Therefore, the loss function will have multiple global optimal that are specified only up to some orthonormal transform. And this function is terribly non-convex. Okay. So a natural question is, what does this optimization optimization function look like? Can we talk about some of these geometric properties? To simplify the exposition, we're going to focus only on the rank 1 case by setting the rank equals 1. And then our parameter space becomes just a vector parameter space that we are now rewriting it as a small x. Therefore, we're going to essentially thinking about this new objective function f of small x, okay, which is also can be thought as some sort of false order polynomial with respect to the vector x. Okay, so what kind of questions we are interested in to understand this non-convex optimization problem? When we start by thinking about where are the critical points, those will be potentially the points that we may converge to if we run some simple iterative algorithms such as gradient descent. And we also want to understand the nature of the critical points. Are they local maxima? Are they local minima? Are they some sort of saddle points? Once we have a good understanding about the critical points, we may then also ask about what the curvature of the loss function look like. That essentially will tell us how we are going to move along the loss function when we run our algorithms. At least we would like to understand the geometry of the loss function locally around the global minimizer, if understanding the entire global geometry is too ambitious. All right, so these are the questions we would like to answer. To begin, let's look at how to study the critical points. Recall that if I'm thinking about arguing about first order critical points, I'll have a critical point if and only if the gradient is 0. Since I know the loss function, I can write down the expression of the gradient and force it to 0. And moving the terms sort of around the different sides of the equality, I can rewrite this condition into one that's corresponding to m times x equals to the square norm of x times x. Sorry. And what this is saying is essentially that x will align with an eigenvector of the matrix M, or x equals to 0. Okay. Since we know the eigenvectors of the matrix M are these ui's with corresponding eigenvalue lambda I, that by proper scaling of the directions, we can find the set of critical points given by the union of the origin plus positive and negative of the scaled eigenvectors. Okay. Now, once we find all the critical points, we want to further categorize the different types of the critical points. The way we're going to categorize them, as we talk a little bit in our preliminaries, we're going to further look at the Hessian of our loss function as the critical points, where the Hessian can be written in this expression. Okay. So now what we are going to do is we're going to pull out the critical points. Let's say we take a non-zero one, and then we're going to plug this into our Hessian expression. With a few lines of calculation, we see that the Hessian actually also admitted very similar eigenvalue decomposition as the original data matrix M, except that the scaling of the corresponding eigenvalues is going to be adjusted a little bit. Okay. Now we are ready to talk about different scenarios about the positive or negative definiteness of the Hessian matrix at different critical points. Specifically, let's assume the spectrum of this matrix M have this property where there is a strict eigengap between the top eigenvalue lambda 1 and the second largest eigenvalue lambda 2. Okay. With this in place, we can see that at the first eigenvalue, as the first critical points corresponding to essentially square root of lambda 1 times u1, which, by the way, we know will be the solution to our PCA problem. At this global optimal solutions, the Hessian is strictly positive definite, meaning that the global minima is also going to be the local minima of our loss function. Okay. Whereas for the other critical points, non-zero critical points, by a little bit of calculation, we can see that the minimum eigenvalue is strictly smaller than 0, but the largest eigenvalue is strictly larger than 0. And therefore, these points will be corresponding to strict saddle points. Okay. Last but not least, at the 0, the origin, the Hessian is going to be negative definite, and therefore it will be corresponding to a local maxima of the loss function. Okay, so with this in place, we can see that the only points that corresponding to the local minima are exactly the ones that corresponds to the solution of our PCA problem, therefore the global minima. While the other critical points are either strict saddle points or local maxima. And this really implies the following good news, right? Where the landscape is indeed benign, where essentially, if you plot the loss function for the one we have on the slide, for this toy example of a two-dimensional setting, we see that all the global minima are essentially are also the only local minima we are going to have. Whereas for the other critical points, they're either the strict saddle points or local maxima. So that if I'm on this critical point, the other critical points, we can always find some descent direction where the objective function will be strictly decreasing. Okay, so therefore, as long as we can come up with some algorithms that can converge to the local minima, we are also guaranteed to converge to the global minima for this type of problem. Okay. So all this is basically saying that for this PCA problem, even though it looks quite pessimistic and daunting on its surface, it's actually a rather benign non-convex problem that we can solve quite effectively. Hopefully, if we can come up with an algorithm that can effectively land on a local minima. All right. Now, once we have a good understanding about where the critical points are, we're now going to also look a little bit about the curvature of the loss function, particularly around the local minimizers. Okay, so again, if we look at this picture, we see around the local minimizer, the loss function actually has a curvature that looks very similar to a strongly convex function, where we may have hope that it may actually converge quite fast if we run gradient descent in this local neighborhood. Indeed, this is a message that we try to convey in this slide, particularly if we're focusing around the local neighborhood of the global optimal, and then in this L2 local neighborhood, where the size of the neighborhood depends on essentially the eigengap of matrix M of interest. And within this local neighborhood, we can actually show that the Hessian of our matrix loss function is going to be strictly lower bounded by some non-zero quantity and also upper bounded. Okay. And what this is saying is that we can basically invoke what the nice convergence rate of gradient descent that we talked about earlier. And if we run gradient descent in this local neighborhood, then our gradient descent iterates will converge to the global optima at a linear rate, where the rate is essentially depends on both the eigengap, the ratio of the eigengap, and the largest eigenvalue. Okay. And this local neighborhood is often called the basin of attraction in the literature, which means once your iterates lands into this basin, it will basically converge linearly to the global optimizer, and you will never jump out of this basin of attraction. All right. So far from this PCA problem, we essentially can abstract out two vignettes for attacking a non-convex optimization problem. The first vignette is what we typically call a two-stage approach. So in this approach, we're typically going to try to come up with some good initialization, typically using the method such as the spectral method, where we hope the initialization will fall into this basin of attraction. And once the initialization is in this basin of attraction, we can run some simple algorithms such as gradient descent or alternating minimization, or some other algorithm of your favorite choice to do some local refinement. Hopefully, this local refinement will converge quickly to the optimal point of interest. Okay. On the other end, there is another paradigm that focuses on analyzing the global landscape. And in this approach, typically, people will extract some nice geometric property, or where, for example, all the local minima are also global minima. And the only type of other critical points beyond local minima are strict saddle points. And therefore, as long as you can come up with some good algorithms that can escape strict saddle point and converge to local minima, you can essentially ensure the global convergence of this non-convex approach. Okay. For the sake of this tutorial, we are only going to mostly focusing on this two-stage approach, where we are going to highlight the spectral method for initialization and going to highlight approach of gradient descent for local refinement. Nonetheless, the second approach that focuses on global landscape is also a quite significant approach that we are going to maybe use a couple of minutes just to briefly talk a little bit about it. So often in this global landscape type of approach, there is a separation between the analysis of the optimization geometry, which are typically problem dependent, that for a given problem, you are going to try to certify two types of properties. The first property is that all local minima are going to be also global minima. The second property is that for the rest of the critical points, they're going to be strict saddle points. Okay. So these properties have been verified for a growing number of problems, such as the earlier principal component analysis problem we use as a toy example, but also more sophisticated problems such as dictionary learning, multi-channel blind deconvolution, and so on. Okay, and this analysis, as I said, is often highly problem dependent. The second step that is often decoupled from the problem is more algorithm specific, that focus on designing algorithms that can probably escape strict saddle points, and often known as saddle point escaping algorithms in the literature. This includes algorithms such as trust region methods, perturbed gradient descent methods, perturbed stochastic gradient descent type of methods, and so on, where this perturbation usually kick in to add a little bit noise in the vanilla search direction of a gradient or stochastic gradient. You may wonder whether the perturbation is indeed necessary. From the literature by a paper by Jason Lee et al., we know that if you run vanilla gradient descent, you are going to guaranteed to be converged to a global minima with probability 1. However, we do not know explicit convergence rate for the convergence vanilla gradient descent for this generic setting. And the perturbation, and indeed there are problem instances where vanilla gradient descent may take exponential time to escape all the strict saddle points in the parameter space. And therefore perturbation is often found useful at least from the theoretical perspective, to ensure some finite time convergence guarantees. To conclude our very short discussion about global landscape, I encourage you to check out the very recent overview and also very nice one by Zhang, Qu, and Wright on the particular topic on this type of landscape analysis, where they particularly highlighted the role of symmetry and symmetry breaking in leading to tractable non-convex optimization solutions to these challenging non-convex problems. Okay, with that, I'll conclude the first part of this tutorial.